Alright, so tonight we are going to start our next module, which will be covering the next lab. So in this module we learn about a new unit of our board, which is called serial communication interface. Now since you are familiar with the computer, I think you see that every day the computer is being used to communicate with different peripherals like keyboard, mouse, printer. There are so many things, I think we cannot list it. And every single communication you are making, even if it is a USB, if it is a serial port, or if it is a parallel port, is some kind of communication, okay? And there are some modules we have in our board which is dedicated to this kind of communication, okay? So one such communication is called serial communication. Now the formal name of this unit is Universal Asynchronous Receiver Transmitter. Now by the name you can see that this is an unit which basically can receive or send the data in plain English, okay? Now remember at the very beginning we showed you this layout of our board, and I tried to circle the red. Do you see the red circle there? That's the module we are talking about right now. And in this module we basically have only two lines. One is TXT and another one is RXT. So one is for the reception and another one is for the sending. Now as you can see from the line, that's just one single line and you are sending the data. Now what do you do in general? You have like 1 byte. Now how do you send 1 byte in one line? You just send 1 bit at a time. Basically in 1 byte you have 8 bits, right? But you'll be sending only 1 bit at a time. So this kind of communication is called serial communication. And if you look at here, the port D pin 0 and port D pin 1, those are your basically the transmission and receiving line for this unit. When you go to the lab, we'll be using these two pins to send the data and to receive the data if we use the serial communication interface, okay? Again, before we start this module, we just want to make sure that this is not the only way of communication. There are another way which is called parallel. This is the serial one. So if you try to compare the serial and parallel, first of all, the serial you have just one line. So all the data you'll be transmitting using just one line. So basically 1 bit at a time. But in parallel, you at least will have like 8 lines, because you will be transmitting 1 byte at a time, because in one line you will be transmitting 1 bit. So it might look like that the parallel has, is much better than serial because it's faster. But the serial has a lot of advantage as well, because if you have a long transmission line, we most of the cases prefer serial than parallel, because you may not have the flexibility of running like 8 lines between like two destination of like 1 mile apart. You see what I'm saying? You cannot run probably 8 lines. So serial communication is quite important. It's really even interesting to understand it if you really want to understand the basics of transmission. So we try to also compare here that how a serial communication and parallel communication is done. In case of serial, you just transmit 1 bit at a time. So you just put all the bit in the queue and do 1 bit at a time. In case of parallel, you at least have 8 lines, so you are transmitting in 1 bit in 1 line, so you are basically transmitting the whole byte at once. But remember, in this lab, for this unit, we'll be only talking about the serial communication, okay? And also, as I said, there are the unit we have is called asynchronous unit. The reason this is asynchronous, because there is no time synchronization between the sender and receiver, because there are a lot of transmission in the world where the receiver and sender, they have some kind of synchronization between them. What do you mean by synchronization? By synchronization I mean that they know each other's time. they have some kind of internal clock. For an example, in my clock, current time is, let's say, 9 o'clock, okay? And let's say I am the sender. And the receiver knows that I'll be sending at 9 o'clock, and it should receive the data at 9 o'clock 1 second. You see what I'm saying? So for some reason, if it doesn't receive at 9 o'clock 1 second, it will probably disregard the data. That's kind of communication where both of the party have some kind of clocking. It's called synchronous. But in case of asynchronous, there is no such thing. The only verification is done using the data. Data itself has some kind of checking, and using that, a receiver always checks whether it received the right byte. Maybe you are sending B8 and you receive B6. You see what I'm saying? So that's what I'm saying. So there is there are some kind of checking. We'll talk about that a little bit about as well. So our communication unit is serial asynchronous. And there are two subunits, receiver and transmitter. Transmitter is the one which is responsible for sending. Receiver is the one which is responsible for receiving. Now it depends on whether it's in receiving mode or it is in transmission mode. Okay? It's basically you are the one who will be writing the code to set it up. The interesting part is, just like the other thing we did in this class, we'll be still writing the code to configure and initialize this module and to make it work. All you need to do is just write the code. We need to know how to do that. Okay. So before we go to those kind of discussion, let's look at a little bit about the data formatting. As I said, we are sending only one bit at a time. But the bit is the whole thing. Whenever you are sending a byte, there are some extra bytes we add with that to before we send. We add a start bit, we add a stop bit, and sometimes we also add a parity bit, just like this. If you look at this one, for an example, look at the bottom one. Let's say this is D7, right? I think we all know this is D7 in binary, right? Now, how the data is sent. Before you send, we add some bits here. Now look at this. Data starts from the least significant bit. So you are basically starting from the backward. If you try to read from the back side, how you start? 1 1 1 0, right? Look at how we are sending, because we send the least significant bit first. Okay? So the bit 0 is being sent first, but before the bit 0, we use a start bit, and the start bit is always a 0. In general, when there is a communication line, in general it's always high. Okay? So whenever the line is a constant high, the receiver knows that there is nothing being sent. But before you start, you always start with a bit 0. You know what I'm saying? Because that's how the receiver knows something is coming right now. So that's why the start bit is always 0, and there is a stop bit which is always 1. So we add the start bit and stop bit. We also sometimes add a parity bit. If you see, at the end of the data, we added a parity bit. Now the parity bit, the reason we add the parity bit is for checking the data. Whenever the receiver receives the data, it can check the data using the parity bit. Now let me tell you how it checks. There are two different kinds of parity. One is called even parity. Now in case of even parity, what happens that whenever the receiver receives it, it just checks whether there are even number of ones in the data. Now you might be wondering how you always can make total number of ones even. The only thing that you can do is you can just set your own parity bit. For an example, what the receiver does is it either set the parity bit as 1 or 0 based on how many ones we have in the data. If the number of 1 is even, the parity bit is what? 0, because it's already even. If the number of ones is odd, the parity bit becomes 1. That's how you always have a even number of ones. That's what I'm saying? And your receiver knows, doesn't matter what it receives, the total number of one should be even. This is called even parity. And the same is, there is a thing called odd parity, meaning the total number of one will be always odd. So sender set the parity bit just like that, the way such that the total number of ones become even or odd. So that, and the receiver and sender already knows that they are using whether the even parity or odd parity. Okay, so that they can check whether the data they received is, even after checking something like this, still there is a chance that your data is messed up, because you might have 2 bit messed up, 1 might be lost. And what happens if 2 ones are lost? Still you might have even number of ones. You see what I'm saying? If only one bit is lost, let's say is one bit 1 is gone, so even number of ones become odd. So receiver knows that the data is messed up. But what happens if 2 ones are lost? So still there is a chance that he might not get the right data. Now, when we send, we also have some other parameters to understand. For an example, we sometimes try to say, okay, we are sending the data. Now, what is the speed of the sending? What is the speed of the transmission? Okay. To do those, we use some kind of some terminologies like this. For an example, let's say we use some of those called, for an example here, if you look at this example, you'll see, I tried to show you some example. For an example, the bit time. Now the bit time means the time you need to send one single bit. Okay. There is one thing called character time. That means the time you need to send the whole data, including the start bit, stop bit, parity bit, everything. Now for an example, I tried to show you that same example here again. Remember the example we had? We have like 11 bits here, right? Can you count how many bits you have? You have 8 data bits. There is one start bit, right? There is one parity bit, and there is one stop bit. How many you have? 11, right? Now look at this. We use the total bits in the word. This is called the word, the whole, data with the start, stop, and all the bits. That's called the character. I'm saying the total bits in the word. So total bits are 11, and the bit time is, you already calculate the bit time. So that means you know that how much time you need to send one bit. If you multiply that by 11, so you will know exactly the character time. That means the time you need to send the whole thing. And then there is another parameter called bit rate. Now that means how many bits you are sending in 1 second. Sometime you may include the parity, or sometime you may not. So, and this is the formula. So total number of bits divided by the bit time. So in the quiz we will try some of this, something will be given and we have to calculate the rest. We'll see that. Now at this point we are trying to explore the serial communication units, right? Remember, so far we have explored a lot of registers like accumulator A, accumulator B, index register X, right? Stack pointer SP. All of those registers we have used so far, those are called general purpose registers, because those are used for pretty much every single thing you do using the register. But there are some special registers with each and every modules we are talking about, or will be talking about soon. Okay. For an example, in the serial communication interface, serial communication unit, we have 5 registers. So here is the list of all the registers, and we'll be exploring one at a time. So I'm not going to talk all of these together, but we'll show you that what we need when. Okay. So these are the names of 5 different registers we have here, and all these registers are only meaningful when you are using the serial communication interface. If you are not doing any kind of serial communication, you probably will not be using any of this register. You know what I'm saying? Because these are only purposefully created just to just to work with your serial communication interface. So these are some, we'll talk about, different register different time. I'm not going to explain all of these because we'll probably need one at a time and we'll talk about those. So I'm just trying, I tried to list you all these, and just one single thing is, if you look at all this slide, you will see that each and every register has a different address. Okay. For an example, this is the serial communication control register 2. If you look at here, the address is 102D. Now how do I get this address? This is predefined. Okay. So it's not like I'm the one who found it, because this is already mentioned in the Motorola handbook provided by the Motorola. Okay. But the interesting part is, just like any other memory location, you can use it as a memory location, and if you are trying to save something into this location, you will end up saving into the register. You see what I'm saying? So that makes our job easy, because you will be just using the same instruction that you used before, like LDAA or STAA and all those instructions to save things here. Pretty much the same kind of instructions, because whenever you will be writing the code, it will look like that you are just working as a memory location. But this location is not a regular memory location, because this location is reserved for the serial communication control register 2. You see what I'm saying? So that's how each and every special purpose register has an independent address. But you can use this address just as a regular address. Okay. So now let's say you are trying to read a register. How do you read it? Just like, I showed you an example. All you need to do is just write one single line. LDAA SCS. And now what you are doing? You are reading what you have in the status register, meaning you are basically taking the data and you are copying to your accumulator A, right? It doesn't have to be accumulator A. You can use accumulator B as well. Now this status register has a special purpose. It's pretty much similar like our flags. Remember, whenever we are doing some operation, and then based on our operation some flags are set and some flags are cleared. Similarly, status register is the one where we have different bits which might be set or cleared based on what we are doing. You see what I'm saying? And to clear the register, especially only the status, I'm talking about only the status register. To clear the register, all we do is we just read the data from the status register, just like writing this one line. And whenever you read it, the status register is cleared automatically. The whole register is cleared, meaning it's replaced by 00 in hex. Now let's say you are trying to write into some register. Now for an example, we have one register called serial communication data register. Now this is the register where you will write your data, that data, the one that you are trying to send. Now let's say you are trying to send something to another computer. Okay. Now before you send it, you have to write it to this register. Now the question is, how do you write it? Only thing you need is to just write these two lines. In first line, let's say you are trying to write, or you are trying to send 7A. What do? You first store the 7A into accumulator. It doesn't have to be accumulator A, it can be accumulator B as well. I just gave an example with A. Okay. Now we first load the 7A into accumulator A, and then we are just storing that byte, meaning we are storing the 7A, because at this point in the accumulator A you have 7A, right, which is already loaded. Now you just stored that 7A from your accumulator to serial communication data register, which is pretty straight, because it's nothing new to us, because it's just like you are storing something to some memory location. You see what I'm saying? But remember, this is not an ordinary memory location, this is a register, which is a special purpose register. But the good thing is, you are still writing the same kind of lines that you have written before. So in the next step we'll see, because as I said, since we will be doing some kind of transmission or reception, right, and there will be two different two different devices. For an example, let's say you probably transmitting data between your board with the computer we have here in the lab. Now, whenever we are talking about any kind of transmission, we might have to set up some kind of speed, right? I'm saying we have to define it, that what will be the speed of the data, and you know, every machine has a restriction. It cannot probably go beyond that speed, but you can probably do it lesser. I'm saying you can probably transmit it with a lesser speed. Now the question is, how do you set that speed? Now I tried to show you some example here. Now for an example in the lab, for an example, let's say you are trying to set the baud rate. Now what is the baud rate again? Number of bits you transmit in 1 second. Let's say in 1 second you are transmitting 100 bits. So that means the baud rate is 100 bit per second. Now let's say here I tried to show you an example that let's say I am trying to set a speed of 9600 bps for a microcontroller of 8 megahertz. Now what does it mean? It means that I have a machine just like the one we have in the lab. Speed of the microprocessor is 8 megahertz, and I'm just trying to communicate with some other device using this machine, and also I want the baud rate 9600, meaning I want to transmit or receive the data at a speed of 9600 bps. Now what does it mean by 9600 bps again? Meaning the transmission line at max can receive 9600 bits per second, which is a huge speed. Now the question is, how do I set it? As I said before, you will be doing every single thing just by writing codes. So you clearly need to understand how to write the code. Now to do that, we need to take the help from some of the tables we have. These tables we have in the Motorola handbook. We have a soft copy of the handbook we gave you under the content section. Now this is the table 7.1 from that book. So and also we have to load some data basically into a register called baud register. Remember I showed you at the beginning that there are 5 different registers. We did not explore any of those yet. So let's say this is the register we need for this purpose, which is called baud register, B-A-U-D. Now how do I set it first? Now look at the configuration you need. You need 9600 and your processor speed is 8 megahertz. Now from the table I tried to identify the 8 megahertz column. Do you see the 8 megahertz column here? And also see 9600 in the column. So we are done. So you got the speed, right, for 8 megahertz. All you need to do is you have to identify the 3 bits at the same row. So you go the back side of the, I'm saying the left side of the table, and you got the 3 bits, and those 3 bits should be going to these 3 locations. Now how do you take those 3, I'm saying those 3 to this location? You can just write 2 lines of code like this. Look at this, what we are doing. I'm just writing the whole byte. Excuse me. I'm just writing the whole bytes starting from the left side. So look at this. Every single bit will be 0 except these 3, right? I tried to mark those as red. Do you see the difference here? I'm just, you know, those are the only 3 bits which we are putting there to set up the speed of 9600. Do you see what I'm saying? So that's the byte we are trying to load into accumulator A, and then later from the accumulator A we are just storing the data to which register? This is the register, right? The baud register. And that's the simple thing we can do. Just write the, you know, we have to look at the table, and then we have to find which beat, meaning which speed we have. If we find the speed, we know the beats that's already given in the table, and then we just write the 2 lines just based on that. Any question here? Now let's look at a little bit additional stuff here. Now let's say I try to show you another example. Again, a similar example, but now we have a microprocessor of 4 megahertz, let's say, and we are trying to set up a speed of 2400. So let's start with using the same step. Now if you look at here, so this is our column for 4 megahertz, right? But if you look at the first table carefully, look at carefully, there is no 2400 here. Do you see any 2400 here? So there is no 2400 here. Now the question is, how do you set it? You have to set it as 2400, right? So what you can do is, you can select something and then divide it by something else. Now for an example, if I do this, I could not find 2400 here, and which is possible, but what I can do is, I can select 4800 from here, and then later I can divide it by 2, right? Because if you divide 4800 by 2, you get 2400, right? Now how do you divide? So to divide it, you need another table. Now we have 2 tables here. Now let's see how we can do it first. Now first I select this 4800, and that's why I'm just taking this, I'm just copying these 3 bits, right, to this 3 location. But I'm not done yet, because I'm not looking for the speed 4800. I'll be dividing it by 2, right? Now to divide it, I'll be selecting the divider. Now here in the second table, the divider I'm selecting is 2, right? Because I'm going to divide it by 2. Now to select the divider, I need to choose 3 bits from the left side, and look at this, how these 3 bits are going. These 3 bits are what? 0, 0, 1, and these 3 bits are for the division. You see what I'm saying? And these 3 bits are for 4800. So now what you did is, you have chosen 4800, and then you selected a divider of 2. That means your speed becomes 2400. Now how do you write the code for this? You will be still doing the same thing. Look at this. Now you have chosen 6 different bits, right? 3 bits from the, look at the leftmost 3 red bits. These are chosen from the first table, right? And the last 3 bits you have chosen from the second table. Remember, this location of the bits are important. You cannot move the bits, because those positions are reserved for that purpose. Last 3 bits are for the divider, and the rest is pretty simple. You just load it to the accumulator. It may be accumulator A, it may be accumulator B, and then you store it to board register. Okay. So we are not done yet, but we still want to understand a little bit more, because we just started with the serial communication interface. But I'll give a pause here so that we can finish the first 2 quizzes first, and then we'll start over from here. We'll start again from here, okay? So to understand the remaining part, because we just started, let's see whether we can understand whatever we covered so far. So now we'll go to quiz section in pause. We have in total 5 quizzes for this module. Once we are done with all the 5 quizzes, we'll go to lab and we'll just modify the software for the lab 3, because for the lab 3 we don't have to modify any hardware, because we already built the hardware for lab 2, and that's exactly what we need for the lab 3. But for lab 3 we have to do some modifications in the code. To understand the modifications, we have to understand pretty much every single example we are trying to give you here, okay? But also we can practice those examples. Now let's go to pause. So far whatever we have covered, you can try 2 quizzes, the quiz 11 and quiz 12, okay? And the remaining 3 quizzes, we'll talk about those after we are done. So let us give a pause here. So let's start again.